Welcome to ZypherSpaceCore. Today we begin our number theory series, the mathematical foundation behind modern cryptography. Before algorithms like RSA, Diffie-Hellman and digital signature can secure the internet, they all depend upon one thing, mathematics. In this series, we will learn how concepts like divisibility, prime number, modular arithmetic, GCD, and the Euclidean algorithm becomes the core of real-world encryption system. In this episode, let us build foundation of computational number theory step by step and understand how mathematics protect digital communication. Every modern encryption system is built on mathematical problems that are easy to compute but extremely difficult to reverse. That one idea is the reason the cryptography work. Let's take an example of RSA. In RSA, we choose two large prime number P and Q and multiply them n equal to P into Q. This multiplication is very easy for computers, but if an attacker only knows n, finding the original prime, that is P and Q, becomes extremely difficult when these numbers are large enough. This problem is called integer factorization, and RSA security depends on it. Now look at Diffie-Hellman. Here we compute g raised to x mod p. Again, computing this value is easy and reversing it, that is, finding x from final result, is computationally infeasible. This is called discrete logarithmic problem. Even digital signature and AES internally depend upon modular arithmetic, inverse, and prime field operation. So, before learning advanced cryptography, we first need to understand mathematics behind it. Now, let us start with the divisibility. A divides B. It means B equal to A into K for some integer K. K should be whole number with no remainder. Let's take an example. 2 divides 10. 10 equal to 2 into K. 10 equal to 2 into 5. So here K equal to 5, which is an integer. So 2 divides 10 perfectly. Now let's take another example, that is 3 divides 10. 10 equal to 3 into K equal to 10 by 3, which becomes 3.333, which is not an integer. So 3 does not divide 10. And this connect directly to modular arithmetic. P mod A equal to 0 implies A divided by B. If remainder becomes 0, divisibility exists. Now let us understand four important properties of divisibility. First one, transitivity. If A divides B and B divides C, then A divides C. Let's take an example. 2 divides 8 become 2 into 8 equal to 2 into 4. And 8 divides 24 become 24 equal to 8 into 3. This automatically becomes 2 divides 24 because 24 equal to 2 into 12. This chaining property appears often in cryptographic group structures. Second one is linearity. If A divides B and A divides C, then A divides B plus or minus C. Example, 2 divides 10 and 2 divides 6. Then 10 plus 6 equal to 16, 10 minus 6 equal to 4. 2 divides 16 and 2 divides 4. So that property is satisfied. Third property is scaling. If A divides B, then A divides B into M for any integer M. Let's take an example. 3 divides 12. Multiplying 12 by 5, that is 12 into 5 is 60. 60 equal to 3 into 6, 20. So 3 still divides the result. Fourth property is division algorithm. Every integer can be written as B equal to AQ plus R, where Q is the quotient, R is the remainder, and R is greater than 0 and less than A. For example, 17 equal to 55 equal to 5 into 3 plus 2. Here quotient is 3 and remainder is 2. If remainder becomes 0, divisibility exists. Now let us move to prime number. A prime number is a number greater than 1 having exactly two divisors, 1 and itself. Examples like 2, 3, 5, 7, 11 are prime numbers. Let's take 7. The only number divides 7 perfectly are 1 and 7. No other divisors exist. So 7 is prime. Now take 10. 10 can be divided by 1, 2, 3, 5, 10. More than 2 divisors exist. So 10 is a composite. Now comes one of the most important theorem in number theory, that is fundamental theorem of arithmetics. This theorem states that every integer greater than 1 can be uniquely written as the product of prime number. The important word here is uniquely. It means every number has its own prime factorization. No matter how many times we break the number down, we always end up with same prime factors. For example, 12 is equal to 2 square into 3, 60 is equal to 2 square into 3 into 5. So every composite numbers can ultimately be reduced into primes. This idea is extremely important in cryptography because RSA security is directly connected to prime factorization. In RSA, we generate n equal to p into q, where p and q are very large prime numbers. Multiplying them is easy for computers, but if someone only knows n, finding the original prime numbers become computationally infeasible when the values are extremely large. Modern RSA commonly use 2048-bit number, and currently no efficient algorithms can factor such huge value in polynomial time. That difficulty is what gives RSA its security. Now let us move to GCD, greatest common divisor. The GCD of two numbers is the largest integer that divides both numbers perfectly. That is GCD of a comma b equal to d, where the d is the largest common divisor of both numbers. For example, GCD of 14 comma 18 equal to 6, because 6 is the largest number dividing both 18 and 48 without remainder. Now look at some important properties of GCD. First one is GCD of a comma b equal to GCD of b comma a. The order doesn't matter. Second, GCD of a comma 0 equal to a, because every number divides 0. GCD of a comma 1 equal to 1, since 1 share no greatest divisor with any number. The another important concept is co-prime numbers. If GCD of a comma b equal to 1, then the numbers are co-prime. This property is extremely important in RSA because the public exponent e must satisfy GCD of e comma phi of n equal to 1. Without coprimality, modular inverse computation will fail. Now instead of finding divisors manually, we use Euclidean algorithm for efficient GCD computation. The key formula is GCD of a comma b equal to GCD of b comma a mod b. We repeatedly replace the pair until the second value becomes 0. Let us understand the flow using GCD of 48 in comma 18. First one, 48 mod 18 equal to 12. So GCD of 48 comma 18 equal to GCD of 18 comma 12. Next, 18 mod 12 equal to 6. So the GCD of 18 comma 12 equal to GCD of 12 comma 6. Then 12 mod 6 equal to 0. So the GCD of 12 comma 6 equal to GCD of 6 comma 0. Once the second number becomes 0, the GCD of the number is, so the first number is the GCD. Therefore, GCD of 48 comma 18 equal to 6. The reason this work is based on the important theorem. Any common divisor of A and B is also divisor of A mod B. So the GCD remained unchanged and during this reduction step. Now we move to extended Euclidean algorithm. The normal Euclidean algorithm only finds GCD, but extended Euclidean algorithm also finds coefficient x and y satisfying ax plus by equal to GCD of a comma b. This equation is extremely important in cryptography because it helps compute modular inverse used in RSA. Using extended Euclidean step GCD of 48 comma 18 We eventually work backwards using backward substitution. After substitution and simplification, we get G6 equal to minus 148 plus 3 into 18. That comparing with ax plus by equal to GCD of a comma b, we obtain x equal to minus 1 and y equal to 3. Finally, by verifying 48 minus 1 plus 18 into 3 equal to 6. Now let us understand modular inverse. Modular inverse of a number a modulo m is a value x such that a into x congruent to 1 mod m. The inverse exists only when GCD of a comma m equal to 1, meaning the numbers are co-prime. For example, finding the inverse of 3 modulo 7 means solving 3x congruent to 1 modulo 7. Using extended Euclidean back substitution, we obtain x equal to minus 2. In modulo 7, minus 2 equal to 5 mod 7. So, 3 inverse equal to 5 modulo 7. Because 3 into 5 is equal to 15. 15 mod 7 equal to 1. And now in RSA, the modular inverse used to compute the private key. If E equal to 7 and phi of n is equal to 16, we compute D equal to E inverse mod 60. Using extended Euclidean algorithm, we get D equal to 3. Verifying 7 into 43 equal to 301, 301 equal to 5 into 60 plus 1. So therefore, 301 congruent to 1 mod 60. Without modular inverse computation, RSA decryption cannot work. So in this episode, we built mathematical foundation behind a modern cryptography. We explored divisibility, prime number factorization, GCD, Euclidean algorithm, extended Euclidean algorithm, and modular inverse. These concepts are not just theoretical mathematics. They are the core building blocks behind RSA, digital signature, secure communication system used across the internet today. So thank you for watching ZypherSpaceCore.